centrally located in the city and nestled in the scenic Varta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Varta River, enhancing the vibrant student life where students can pursue their passions. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 60 degree programs, including 20 taught in English. The university attracts over 1,500 students from 5 continents and 80 countries. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short-term and long-term exchanges. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short and long-term exchanges, offering invaluable international experience. Poznan University of Technology is the only public university in Poland that leads the European University UNIS, a consortium that brings together 10 universities from across Europe. Students can also take advantage of numerous courses and internships offered by the consortium's member universities. The university offers opportunities for further development through 30 postgraduate study programs. There are over 300 doctoral students conducting research in the English language doctoral school, while more than 300 participants are enrolled in postgraduate studies. The high quality of scientific research at the university is confirmed by the latest categorization performed by the Ministerial Science Evaluation Committee. Poznan University of Technology is also a welcoming environment for creating business ideas and developing startups, serving as a hub for transferring the latest knowledge and technologies into practical applications. The university's potential is reflected in 1,300 research and teaching staff members who are involved in both national and international research projects. The university conducts nearly 1,000 research topics with expenditures close to 200 million PLN. Approximately 5% of the research staff is annually listed among the top 2% of the most influential scientists in the world, according to Stanford University. In addition, the university secures grants from nearly every available funding path in Poland and Europe, including ERC grants. Poznan University of Technology is a highly reputable institution with a well-established position and reputation. In the 2024 Perspektywy ranking, we were ranked in the top 10 overall and 5th among technical universities. Poznan University of Technology is the only university in Western Poland with an aviation training centre that includes a fleet of training aircraft. Here, innovation meets reality. Two of the investment projects being developed at the Konkolewo campus, the Space Robot Testing Centre and Earth Surface Imaging, have been selected by the European Space Agency as laboratories where students from ESA member countries will undertake internships. This is where technologies for future space exploration missions will be tested. Additionally, Poznan University of Technology is also the only university in Poland with a photovoltaic farm. Our near-zero energy buildings are entirely based on proprietary technology. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology. Poznan University of Technology. Poznan University of Technology boasts over a century of tradition, seamlessly blending its rich history with a focus on future growth and innovation. The heart of the university's activities is the Varta campus, centrally located in the city and nestled in the scenic Varta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Varta River, enhancing the vibrant student life where students can pursue their passions. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 60 degree programs, including 20 taught in English. The university attracts over 1,500 students from 5 continents and 80 countries. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short-term and long-term exchanges. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short and long-term exchanges, offering invaluable international experience. Poznan University of Technology is the only public university in Poland that leads the European University UNIS, a consortium that brings together 10 universities from across Europe. Students can also take advantage of numerous courses and offered by the consortium's member universities. The university offers opportunities for further development through 30 postgraduate study programs. There are over 300 doctoral students conducting research in the English language doctoral school, while more than 300 participants are enrolled in postgraduate studies. The high quality of scientific research at the university is confirmed by the latest categorization performed by the Ministerial Science Evaluation Committee. Poznan University of Technology is also a welcoming environment for creating business ideas and developing startups, serving as a hub for transferring the latest knowledge and technologies into practical applications. The university's potential is reflected in 1,300 research and teaching staff members who are involved in both national and international research projects. The university conducts nearly 1,000 research topics with expenditures close to 200 million PLN. Approximately 5% of the research staff is annually listed among the top 2% of the most influential scientists in the world, according to Stanford University. In addition, the university secures grants from nearly every available funding path in Poland and Europe, including ERC grants. Poznan University of Technology is a highly reputable institution with a well-established position and reputation. In the 2024 Perspektywy ranking, we were ranked in the top 10 overall and 5th among technical universities. Poznan University of Technology is the only university in Western Poland with an aviation training centre that includes a fleet of training aircraft. Here, innovation meets reality. Two of the investment projects being developed at the Konkolewo campus, the Space Robot Testing Centre and Earth Surface Imaging, have been selected by the European Space Agency as laboratories where students from ESA member countries will undertake internships. This is where technologies for future space exploration missions will be tested. Additionally, Poznan University of Technology is also the only university in Poland with a photovoltaic farm. Our near-zero energy buildings are entirely based on proprietary technology. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology. Poznan University of Technology boasts over a century of tradition, seamlessly blending its rich history with a focus on future growth and innovation. The heart of the university's activities is the Warta campus, centrally located in the city and nestled in the scenic Warta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Warta River, enhancing the vibrant student life where students can pursue their passions. Bicycle paths and recreational areas run alongside the Warta River, enhancing the vibrant student life. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 60 degree programs, including 20 taught in English. The university attracts over 1,500 students from 5 continents and 80 countries. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short-term and long-term exchanges. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short and long-term exchanges, offering invaluable international experience. Poznan University of Technology is the only public university in Poland that leads the European University UNIS, a consortium that brings together 10 universities from across Europe. Students can also take advantage of numerous courses and internships offered by the consortium's member universities. The university offers opportunities for further development through 30 postgraduate study programs. There are over 300 doctoral students conducting research in the English language doctoral school, while more than 300 participants are enrolled in postgraduate studies. The high quality of scientific research at the university is confirmed by the latest categorization performed by the Ministerial Science Evaluation Committee. Poznan University of Technology is also a welcoming environment for creating business ideas and developing startups, serving as a hub for transferring the latest knowledge and technologies into practical applications. The university's potential is reflected in 1,300 research and teaching staff members who are involved in both national and international research projects. The university conducts nearly 1,000 research topics with expenditures close to 200 million PLN. Approximately 5% of the research staff is annually listed among the top 2% of the most influential scientists in the world, according to Stanford University. In addition, the university secures grants from nearly every available funding path in Poland and Europe, including ERC grants. Poznan University of Technology is a highly reputable institution with a well-established position and reputation. In the 2024 Perspektywy ranking, we were ranked in the top 10 overall and 5th among technical universities. Poznan University of Technology is the only university in Western Poland with an aviation training centre that includes a fleet of training aircraft. Here, innovation meets reality. Two of the investment projects being developed at the Konkolewo campus, the Space Robot Testing Centre and Earth Surface Imaging, have been selected by the European Space Agency as laboratories where students from ESA member countries will undertake internships. This is where technologies for future space exploration missions will be tested. Additionally, Poznan University of Technology is also the only university in Poland with a photovoltaic farm. Our near-zero energy buildings are entirely based on proprietary technology. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology. Poznan University of Technology boasts over a century of tradition, seamlessly blending its rich history with a focus on future growth and innovation. The heart of the university's activities is the Warta campus, centrally located in the city and nestled in the scenic Warta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Warta River, enhancing the vibrant student life where students can pursue their passions. Bicycle paths and recreational areas run alongside the Warta River, enhancing the vibrant student life. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 60 degree programs, including 20 taught in English. The university attracts over 1,500 students from 5 continents and 80 countries. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short-term and long-term exchanges. Interest from international students has grown significantly in recent years, with many drawn to the diverse English-taught programs and numerous international agreements that provide opportunities for short and long-term exchanges. offering invaluable international experience. Poznan University of Technology is the only public university in Poland that leads the European University UNIS, a consortium that brings together 10 universities from across Europe. Students can also take advantage of numerous courses and internships offered by the consortium's member universities. The university offers opportunities for further development through 30 postgraduate study programs. There are over 300 doctoral students conducting research in the English language doctoral school, while more than 300 participants are enrolled in studies. The high quality of scientific research at the university is confirmed by the latest categorization performed by the Ministerial Science Evaluation Committee. Poznan University of Technology is also a welcoming environment for creating business ideas and developing startups, serving as a hub for transferring the latest knowledge and technologies into practical applications. The university's potential is reflected in 1,300 research and teaching staff members who are involved in both national and international research projects. The university conducts nearly 1,000 research topics with expenditures close to 200 million PLN. Approximately 5% of the research staff is annually listed among the top 2% of the most influential scientists in the world, according to Stanford University. In addition, the university secures grants from nearly every available funding path in Poland and Europe, including ERC grants. Poznan University of Technology is a highly reputable institution with a well-established position and reputation. In the 2024 Perspektywy ranking, we were ranked in the top 10 overall and 5th among technical universities. Poznan University of Technology is the only university in Western Poland with an aviation training centre that includes a fleet of training aircraft. Here, innovation meets reality. Two of the investment projects being developed at the Konkolewo campus, the Space Robot Testing Centre and Earth Surface Imaging, have been selected by the European Space Agency as laboratories where students from ESA member countries will undertake internships. This is where technologies for future space exploration missions will be tested. Additionally, Poznan University of Technology is also the only university in Poland with a photovoltaic farm. Our near-zero energy buildings are entirely based on proprietary technology. Poznan University of Technology boasts a modern infrastructure where tradition meets modernity. Poznan University of Technology. Poznan University of Technology boasts over a century of tradition, seamlessly blending its rich history with a focus on future growth and innovation. The heart of the university's activities is the Warta campus, centrally located in the city and nestled in the scenic Warta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Warta River, enhancing the vibrant student life where students can pursue their passions. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 6.
Ladies and gentlemen, dear guests, on behalf of the organizers of 6th Polish Biomedical Conference, I welcome you to the Poznan University of Technology. We are glad that you're taking part in this event. We have 2 days of intensive discussions, exchange of ideas, and inspiring meetings. We hope that this conference will bring many new ideas and cooperation and contribute to the further development of biomedical engineering. But this conference will not have been possible without the support of the university authorities. And now, let me invite the Rector of the Poznan University of Technology to the stage. Please welcome Professor Teofil Jesionowski.
Good morning, ladies and gentlemen. I please welcome all of you at this special event, the Poznan University of Technology. Welcome to Poznan. I'm really honored to express, I hope, warm words. Frankly speaking, as you have seen from the video, we are ranked as one of the best universities. We are placed in the 8th place at the all academic university in Poland. We are also proud that we are composite from the 9 faculties. It means 9 schools due to US, let me say, composition, and we are also ranked as one of the best university due to evaluation. It means due to state of art, due to scientific development. Of course, one of the power force is biomedical engineering. So our, let me say, dream is to establish mostly advanced science in this discipline, in this platform. And moving to the university, we are also belonging to the initiative which is named European University. We belong to the UNIS University, but not only belongs because we are leading as only one university, as a public university in Poland, which is also composed from the 10 universities from all Europe. So we cover all geographic area from the Spain to the Finland, from the Sweden to the Greek. So we are really proud. One of the universities, for example, Catania University, which was established in 1434, so quite old university. As you know, we were established in 1919, so nowadays we are celebrating 105th anniversary. Of course, moving to the university, let me express my, let me say, sincere gratitude for to the organizer, and of course for all people that organizing this annual conference. Especially, I would like to emphasize let me say, greetings to the students, because this conference is mostly composed by students, by, let me say, very active person. So I'm really lucky. And of course, let me also share greetings with foreigners and other university, including Poznan universities and also university that surrounded our Europe. I wish you all the best, not only due to development in biomedical engineering, but also due to friendship, due to fruitful, let me say, conversation. And the weather is also quite good. I guess that during the, let me say, evening, you will find also the pleasant state in our city. So I wish you all the best. And of course, our university is all, let me say, all time open to you to create new future, better future for our better life. Thank you very much.
Thank you. And I want to also invite the Dean of the Faculty of Mechanical Engineering to speak. Please welcome Professor Bartosz Gapiński.
Thank you very much. I'm not so experienced, so I need my notes. Magnificent Rector, dear speakers and panelists, dear sponsors and patrons, dear students and lecturers, all distinguished guests, I'm very pleased that the sixth time we can welcome you within the walls of the Poznań University of Technology at the Polish Biomedical Engineering Conference organized by Faculty of Mechanical Engineering. We are gathered here to share the biomedical engineering expertise with students each other, between the specialists such as company representatives, doctors, engineers, and PhD students. I would like to take this opportunity to thank the entire organizing committee who have been preparing this today meeting for many months. It's once again a great job. Thank you very much. And as Mr. Rector, I wish you all many fruitful scientific discussion and networking, and enjoy the conference and social meeting at the evening. Thank you very much. Enjoy the conference.
Thank you. And finally, it's time to welcome the main conference organizer to the stage. Please welcome Natalia Wierzbicka.
Thank you very much, Paweł. Dear Rector, dear Dean, distinguished guests, on behalf of all organizers and myself, I warmly welcome you on the 6th Biomedical Engineering Conference. It's first time when we change the format to the international one. This event, which brings together the science, industry, and medicine, has been possible thanks to the support of Poznań University of Technology, the Faculty of Mechanical Engineering, all patrons, partners, and of course volunteers, which works with us to make these 2 days of conference exceptional. We prepared very interesting lectures, discussion panels, and workshops. Also, you will have the possibility to discuss with representatives of companies. And now I think I should say that I wish you this 2 days will be amazing, and you will have opportunity to get new knowledge and to have new connections between the enthusiasts of biomedical engineering enthusiasts. And now I would like to invite you to the short movie of Poznań Biomedical Engineering and Poznań University of Technology. And after this, we will officially begin the 6th Biomedical Conference. So thank you very much and enjoy your time.
Poznan University of Technology boasts over a century of tradition, seamlessly blending its rich history with a focus on future growth and innovation. The heart of the university's activities is the Varta campus, centrally located in the city and nestled in the scenic Varta riverbed, with excellent connectivity to the rest of the city. The university offers students accommodation in 6 dormitories, along with amenities such as a canteen, student associations, student radio, a library, a modern sports hall, fields and tennis courts. Bicycle paths and recreational areas run alongside the Varta River, enhancing the vibrant student life where students can pursue their passions. The university takes pride in its choir, Volantes Soni, and athletes who earn accolades both nationally and internationally. Poznan University of Technology educates over 14,000 students across 9 faculties, offering nearly 60 degree programs, including 20 taught in English. The university attracts over 1,500 students from 5 continents and 80 countries. Interest from international students has grown significantly in recent years, with many drawn to the diverse English taught programs and numerous international agreements that provide opportunities for short-term and long-term exchanges. Interest from international students has grown significantly in recent years, with many drawn to the diverse English taught programs and numerous international agreements that provide opportunities for short and long-term exchanges, offering invaluable international experience. Poznan University of Technology is the only public university in Poland that leads the European University UNIS, a consortium that brings together 10 universities from across Europe. Students can also take advantage of numerous courses and internships offered by the consortium's member universities. The university offers opportunities for further development through 30 postgraduate study programs. There are over 300 doctoral students conducting research in the English language doctoral school, while more than 300 participants are enrolled in postgraduate studies. The high quality of scientific research at the university is confirmed by the latest categorization performed by the Ministerial Science Evaluation Committee. Poznan University of Technology is also a welcoming environment for creating business ideas and developing startups, serving as a hub for transferring the latest knowledge and technologies into practical applications. The university's potential is reflected in 1,300 research and teaching staff members who are involved in both national and international research projects. The university conducts nearly 1,000 research topics with expenditures close to 200 million PLN. Approximately 5% of the research staff is annually listed among the top 2% of the most influential scientists in the world, according to Stanford University. In addition, the university secures grants from nearly every available funding path in Poland and Europe, including ERC grants. Poznan University of Technology is a highly reputable institution with a well-established position and reputation. In the 2024 Perspektywy ranking, we were ranked in the top 10 overall and 5th among technical universities. Poznan University of Technology is the only university in Western Poland with an aviation training centre that includes a fleet of training aircraft. Here, innovation meets reality. Two of the investment projects being developed at the Konkolewo campus, the Space Robot Testing Centre and Earth Surface Imaging, have been selected by the European Space Agency as laboratories where students from ESA member countries will undertake internships. This is where technologies for future space exploration missions will be tested. Additionally, Poznań University of Technology is also the only university in Poland with a photovoltaic farm. Our near-zero energy buildings are entirely based on proprietary technology. Poznań University of Technology boasts a modern infrastructure where tradition meets modernity. Poznań University.
Dear guests, now we can start the first part of our conference, and this will be session number 1, Biomedics. And on this part, the speaker will be Associate Professor, Doctor of Engineering, Sofian Gena, who represent Université Polytechnique Hauts-de-France-Valence. I hope that I spell it on good way. And the speech title is Bio-Inspired Design and MEMS Technology in Miniature Flying Robots Fabrication and Dynamic Testing. And maybe I will introduce you, because it's a lot of things to say about you. Sofian Gena received an engineering degree in electrical engineering in 2011 from the National Polytechnic School of Algiers, and a master degree in electrical engineering system from the National Polytechnic Institute in Toulouse in 2012. And finally, the PhD degree in electrical engineering from Lille University in 2016. After 1 year as a temporary teaching and research assistant in Lille University and 2 years as a postdoctoral researcher in Paris, he joined Université Polytechnique Hauts-de-France-Valence as associate professor in September 2019. His research interests include the design, modeling, and control of smart materials-based actuators, microsystems, and bio-inspired systems. And before our speech, I want to remind one thing. Don't forget to prepare questions for our speaker after this speech. And please remember about the knowledge competition after every speech and during this conference, during every speech. So, stage is yours.
Thank you very much, sir. Hello, everyone. First of all, I would like to thank you for inviting me to this conference. And I would like to add one information to say that my lab is IMN for Institute of Electronic, Microelectronic, and Nanotechnology, which is located in the north of France. And today I'm going to be talking on bio-inspired design and MEMS technology in miniature flying robots. We will see fabrication and dynamic testing. For this reason, great. I decide to share my presentation on 4 axes. First, an introduction to explain how nature, particularly flying insect, serves as model for designing these miniature robots. Then, we will dive to bio-inspiration, highlighting flight mechanism and how its influence on wing actuation, wing geometry, and wing kinematics. Then we will move to nano-aerial vehicle, where we present our proposed design, given here in this picture. We will discuss its operating principle, manufacturing, and motion analysis, and we will analyze also the produced lift force of these miniature robots. We will conclude by discussing the excitation or future excitation prospect of this nano-aerial vehicle. But first of all, an introduction is necessary to understand why we have proposed this topic. Nature gifted flying insects with incredible capacities that we seek to replicate. They can hover in confined space and demonstrate a great agility and maneuverability. They can work collectively in swarms. Their ability to remain visually discrete and work with low noises make them ideal model for bio-inspired technology, particularly for environment requiring low disturbance. However, replicating these abilities represent significant scientific and technical challenges. Sorry, I think I have some problem. Okay. Flying insects are often in few centimeters in size and weigh mere milligram. The kinematics of their flights and aeroelasticity of their wings are complex, which puts extra demands on their design, especially for hovering capabilities. Energy autonomy, as well as communication functions, are the major hurdles. These technological challenges showcase the advanced fusion of biology and engineering required to mimic insect flight efficiency. We will present some applications of this nano-aerial vehicle. They can be used in several applications, whether for defense or civilian domain, particularly for exploring confined environment. For example, they can be used for searching and rescue missions, such as finding survivors or in disaster zones. Second, they can be used for inspection of hard-to-reach areas, such as industrial sites and damaged infrastructure. Third, they can be used for exploration of hazardous area, for chemical or radioactive zone, where the human access is limited, and for threat detection to identify dangers such as explosive. Technological advancement in defense can drive innovation that enhance civilian capabilities, particularly in high-risk and inaccessible zones. It is a topical issue. For decades, the idea of bio-inspired robots has fueled both research and popular imagination. In 2011, NATO's General Yakovlev described robots will operate in swarms, which requires algorithms capable of making them work collectively. This concept resonates with science fiction, where Frank Herbert, in 1965, June, reported the researcher killer lifted into the air and began to oscillate. In 2003, Michael Crichton said in his book, they had thought of something the size of dragonfly. And similarly, in 2001, Dan Brown said, this micro-robot, a miniaturized electromechanical system, the technology of the fly on the ceiling. As we can see from science fiction, it becomes a reality of these visions highlight how convergence of technology, can come back. I think it's not working very well, this one. Sorry for that. I know what happened. Okay. Okay, it's okay. Thank you. In this graph, we will show the relationship between the mass and the wingspan of artificial insect. And let's start with this prototype, which is a festal, is a kind of butterfly. It has the largest wingspan. Yeah, please. Yeah. And excitation frequency, it was 5 Hertz. And second one is hummingbird with a medium wingspan. And excitation frequency of 20 Hertz. The third one is a Dolphin, a prototype with around 10 centimeter in wingspan and few grams. And the latest of all these prototypes are RoboBee, given here in this video. Our objective is to provide a nano-aerial vehicle in few centimeters as wingspan and a mass. And this shows the evolution of bio-inspired design and how scale and material choice impact aerial performances. Now let's focalize on this blue rectangle. Here in this graph, on the right side, we have Vespa volutina, and on the left side, we have Drosophila. And now we will present the most important prototype between those extreme, and we can cite, for example, the wood prototype in 2007, which is based on piezo actuator technology, and the second one, Zoo model in 2016. And in 2018, we have 2 prototypes, JAMS, and 4 prototypes. The 4 prototype is provided by our lab, IMN. As we can see, our nav is the latest and smallest ever fabricated, and we see the progression toward lighter and smaller design with better flight capabilities. In this figure, we have 2 figures, variation of frequency in function of wing length. On the left side, it gives us an information about the mass of nanodrone, while on the right side, we have an information about the power-to-weight ratio. Milliwatt per gram. Sorry? Directly from here? Okay. Here. Okay, great, thank you. Okay. For example, if we need to design a wing length with 10 millimeters and excitation frequency of around 80 Hertz, we can get a nanodrone with a mass around 10 milligrams. On the right side, information that we can get is for similar conditions, the power-to-weight ratio is around 20 milliwatts per gram. Wing dimension significantly influence flight dynamic, balancing size, and performance in bio-inspired design and natural species. For wing actuation, we have 2 kinds of actuation, a direct and indirect actuation. First, for example, for dragonflies, their wings are controlled by muscles attached directly to the base of the wings. And we can see by this animation how it moves. The second one For example, flies, mosquitoes, and wasps, they use an indirect fly where muscles deform the thorax to generate wing movement, and here is it, an animation for its movement. Here we present different kind of a real wing on the left side to show its influence on the aerodynamic performances, and on the right side we have some artificial wings. Nature's diverse wing geometry inspire innovative design for aerial vehicle, highlighting their role in enhancing aerodynamic performance. For wing geometry, if we analyze the wing of a California, we can see that the membrane thickness plays an important role, and its thickness is in a range of 1 to 8 micrometer, with a main vein of around 40 micrometer. It has an elliptical vein shape. Intricate design of wing structure in nature provides key insight for engineering efficient flight. For the wing kinematics, here in this video, we present a Manduca sexta. We can see the behavior of the wing, and if we analyze this movement, we can see that we have two movements: horizontal beating and rotating movement with a wide angle of attack. Okay. For insect aerodynamics aspects, in this graph, we present the variation of a mass as a function of Reynolds number, and the Reynolds number is the ratio between inertia and viscosity forces. As we can see, for most of aircraft, such as C-5, Boeing 737, and Cessna, they have a higher Reynolds number. However, for butterfly or insects, effectively at much lower Reynolds number due to the unique wing structure and flapping. We can say that the plane is not inspired from insects. Now we present our project for OVMI. In French is Objet volant mimant l'insecte, which means flying object mimicking an insect. And for this project, we are working on several topics. First, structure manufacturing, including microfabrication. Second is studying of the body and wing functioning, including modeling. And the third is concept of the integrated control system. Fourth, we work on aerodynamics, stress, strain, and kinematics, and also on experimentation, source and energy recovery, and also communication modes. The originality of our work is the use of microtechnology for manufacturing and also using vibrating wing concept. Here in this figure on the right side, we have our proposed nano aerial vehicle. As we can see, we have, I don't know how it works. Okay, here we have a wing and main vein here, a magnet. This one is a magnet, the thorax, and the coil, and sepal of the coil. For example, this nano-aerial vehicle is based on electromagnetic actuation. When we give a current, sinusoidal current to the coil, it generates a sinusoidal movement on the magnet. And this movement will transmit it to the wing, generating a movement. This design approach brings us closer to replicating the agility and efficiency of natural flying in ultra-small scales. Now, the question is, where is the ideal position of the magnet in comparison to the coil? In order to find this optimal position, I mean magnet to the coil, we did a finite element simulation using COMSOL multiphysics. And for this reason, we have fixed a coil. The coil is this rectangle, and the magnet is here, is moving, and we did simulation to see which is the optimal position in comparison to the magnet. For electromagnetic force, we can see now the variation of this force in function of magnet position, and we have two maxima, one here and another here. This means that the ideal position is located when the electromagnetic force is higher, and in our case, the maximum force exerted on the magnet is found just outside the end of the coil. Now let's analyze the insect flights and how the wing beats at different angle. We can see that from analyzing this video, we have two movements of the insect. Is this movement, and this movement is produced by two kinds of modes. One is like this, and second one is rotation. And by this way, we generate a lift force. And we see how nature solves the problem of flight. Our objective is to produce this real movement. And here we have simulation of two modes. Of course, after optimizing our design. On the left side, we have flapping modes. And on the right side, we have twisting modes. We designed this nano-aerial vehicle structure to exhibit two wing resonance modes. And our goal is to actuate these modes at specific frequency. If we excite both of them at specific frequency, we can get contribution of both of them. How we can do it? Here, we did a modeling of proposed design, and we have the response of the geometrical structure in function of frequency. As we can see, we have two responses. One is this response, which corresponds to the bending motion, and the other one, blue one, corresponds to twisting modes. If we want to excite both modes, we need to choose a frequency which is in between these two modes with phase quadrature of p/2. There are two driving frequencies that induce quadrature phase shift between the modes, and the motion amplitude is significantly increased due to the resonance behavior. Now, we have those two modes, and if we will excite those two modes in frequency between them, we can get the contribution of both modes as shown here. A combined flapping and twisting motion is obtained, very close to an asymptotic kinematics. The structure produces a natural fluid wing motion that mimics how insects generate lift and maneuver with precision. Sorry, I need to come back here. Yeah. Here we will present the microtechnology, a microfabrication of the nanodrone. We use a microtechnology which is compatible with microelectronics. We use materials such as polymer, SU8, and a parylene for wings. This method is reproducible, simple, and low-cost manufacturing. In terms of characteristics, we have a fully mastered micromachining process in polymer, a fully compliant structure, resonant vibration to increase the amplitude, and we use electromagnetic actuator. As we can see, this prototype has span lower than 3 centimeters with weight of around 20 milligrams. Before explaining how we produce this prototype, in our IMN lab, we have a clean room, and in this clean room, we have different units. For example, for lithography units is a process, or lithography is a process that gives the capability of patterning material at micro and nanometer scale. And for this, we have 3 main steps. The first one is coating, and then expose, and then develop. For example, the first step is to make the deposition of the photoresist here, and by spin coating, if we control the speed and the acceleration, we can control the thickness of the layer. And second is expose. A patterned mask is applied to the surface to block the light. And in this case, we have 2 kinds. If we use a photoresist, a positive photoresist, we will remove the material here and here where it is insulated. However, if we use a negative photoresist, we will keep a material at the place where is insulated here. And by doing some development, we can obtain our prototype. And now, let's present the microfabrication process of this microdrone. Here we have our nano area vehicle, and we will make the deposition of the sacrificial layer, which is omnicoat on all the wafer. Here we have a wafer with 3 inch. And now we make the deposition of the first layer of SU8. And then we need a mask, patterned mask, then insulation, expose of the first layer. Second, as the thickness of the nanodrone is variable, for example, from thorax to the wing to the main vein, we need to add other layer. Here we have exposure of second layer. And now it's deposition of third layer for the thorax, insulation. And finally, we obtain this prototype. As we can see here, the provided prototype here is without a wing. Now we need to add a wings. How we can do it is by using evaporation deposition of Parilene C. Parilene C is a transparent material, and now we have deposition on all the wafer. We will add etching mask for deposition of some resin. And now we add a mask for the wings, and we want to keep the material at place where it is insulated. Insulation. And finally, we have etching mask, development of the resin, plasma etching of the Parilene C, and finally, we have our final product, which is given in this figure. On one wafer for 3 inch, we can obtain, for example, 10 prototypes. Now for the assembly of different parts of nano-aerial vehicle, we have a manual gluing of individual parts, and we use a centering element. This means we have some natural clamping. For example, here and here is natural for clamping this part to this. And for the magnet and the coil, we use, for example, a glue. And on the right side, we have the final prototype, and this actually is excited by using a wire for exciting the coil. A summary of prototype, wingspan of 3 centimeters and weight of around 20 milligrams. We use Parilene C for wings and SU8 for other thicknesses for the nanodrone. We have flexible structure. We use electromagnetic actuator. We have extremely lightweight, emulating the natural flyers. In this video, we have excited the nanodrone at a given frequency. This frequency is in between two resonant modes. And now we can see this movement, which is really close to the movement of the insect that we have seen in the video. A bending and twisting motion occurring in quadrature, and we obtain 20 to 30 bit amplitude, and we have a change of wing inclination at the end of each flapping cycle. We have this movement, which replicate really the movement of real insect. If you want to see the movement of the magnet in the video, here is the magnet, is moving here and transmit vibration to the wings. Now we need to characterize the performances of this nano-aerial vehicle, and we need to measure the generated lift force. How we can do it? For measuring the force generated by insect, we use Biomedical, for example. We can use immense piezoresistive force probe, for example, for the case of the ants or the cockroach. When it walks, it measures the variation of some electrical resistance and give us an information about generated force. However, this technique is not suitable for flying insect. For flying insect, we use immense capacitive force probe. In fact, when the insect is glued through this beam, when it moves, it gives us an information about generated force. For more detail, we have a kind of internal capacitance. When we move this beam, we will vary the internal capacitance, and if we know its dimensions and this variation, we can obtain an information about the generated lift force. For us, we didn't use these techniques because it is not easy to provide this kind of sensor. We have opted for another technique. Which one? We have used a sample beam. Now, how can sample beam give us an information about the lift force? A free beam or a clamped free beam has been used. And here we have a spot of laser. If we measure the displacement at the end of this beam, and if we know the stiffness of the beam, we can estimate produced lift force, F equal stiffness times displacement. Now, how we can dimension this force sensor? We need to get an idea about the stiffness of the beam, which give us idea about the lift force of the nanodrone. And we need an electrical excitation frequency lower mechanical resonance frequency. Mechanical resonance is when the wind drives the bridge to oscillate at its neutral frequency. We say that they are in resonance. But in our case, we need to avoid disturbing our measurement. Then we need a higher mechanical resonance, and electrical excitation will be very low. We did analytical modeling. We can, for example, now calculate the resonance frequency of the beam in function of internal parameter of the beam, such as thickness, width, Young modulus, and also for the stiffness. We did finite element simulation using COMSOL. And now if we vary the length of our beam, this length, we can get variation of stiffness in function of this length, and now also for the frequency in function of the length. If we need some rigidity, some stiffness, for example, which is suitable of produced force of our nano-aerial vehicle, in our case, we have chosen this kind and the resonance frequency of approximately 800 Hz. For practical characterization, we use an external force sensor. Given here, we will apply a displacement on this beam and measure at the same time the force. If we have a variation of force in function of displacement, we can determine stiffness of our MEMS microforce sensor. For mechanical resonance, we have excited mechanically this sensor, and we have measured the displacement. And now, by applying fast Fourier transform, we can determine the resonance frequency of the beam, which is around 800 Hz. As we can see, practical result is in good agreement with theoretical one. Now we have characterized our MEMS microforce sensor for measuring the lift force. We can now also characterize the generated force by the magnet. And now we have glued the magnet on our sensor, and we use a coil with a given distance between them. And now we have applied a different value of the coil, of the current to the coil, and we measure the displacement, this displacement on the magnet. We know the stiffness of our force sensor, and now we can get an idea about this electromagnetic force. For a given distance between the magnet and the coil, we have now the variation of current and the force. For example, for this level of current, we have an idea about electromagnetic force and so on, and this is given for a distance of 2.5 millimeter from here to here. If we do this work for different positions, for example, 1 millimeter, 1.5, 2, and 2.5, now we can get an idea about electromagnetic force. First, if we are here for all curves, we can get information about variation of this force in function of magnet position for this current. Similarly, for other value, here, or here, or here. As you can see, more the distance is lower to the coil, more the force is higher, as presented by our simulation. Now, for measuring the generated lift force, we have glued this nano-aerial vehicle on this beam, and we use a laser for measuring displacement here. The nano-aerial vehicle is excited at a given current, but by varying the frequency from 120 to 220 Hz. And we measure the displacement produced here. We know the relation between displacement, stiffness, and the force, and now we have several points, several measurements that give us an idea on this generated lift force. As we can see, we have two maxima. One is here, second one is here, which is corresponding to both modes. Sorry. The flapping mode, this one is here, and twisting mode is here. The ideal excitation frequency, in our case, will be here in order to obtain higher lift force. Generated lift force is in the range of 200, around 200 micronewtons. As we have presented, the mass of our nanodrone is in the range of 20 milligram. Then we have generated a lift force in the range of this nanodrone. This means that produced lift force is not sufficient for seeing this nanodrone flying. However, if we increase the value of the current, we can increase this lift force. In this video, we are exciting the coil with increasing the value of the current, and by this way, we can increase the generated lift force. However, we have some limitation here because this coil diameter is with few micrometers, which means that it has some limits in terms of the applied currents. Then we need to think about changing this coil, but maybe we'll increase the weight or using other techniques. In this video, we have the artificial insect which is trying to fly, but is not able for several reasons. First, as you can see, the excitation is given through the key ball. This means that we have an additional friction. And second, sorry, of course, it is attached to this support. If I can show again the video, I know how. Come back and go on. Okay. Here is the movement, real movement of this insect. For actual work, we are working to improve this lift force, generating lift force, and we are thinking about other techniques. The idea is to use structure with compliant link and rigid body. This prototype, and now our PhD student is working on adding some compliant link here and here, and the idea is for amplifying the movement of the wing. On the left side here, we use other Bernoulli beam model for optimizing the geometrical structure, and on the right side, we use equivalence with 0D model, I mean mass and spring model. For here we have a video for a given excitation, and we can see a large amplitude wing beat in comparison to the first one. We also think about adding a second electromagnetic actuator, one here and another one here, in order to increase the movement. And we see we have both modes, flapping and twisting modes, with higher performances. For conclusion, we achieved the world's smallest nano-aerial vehicle. We demonstrated highly precise micromachining capabilities, and we developed bio-inspired insect kinematics using single actuator operating at fixed frequency. We have implemented fully compliant structure enabling resonant motion. As perspective, we are working to enhance this lift force, to enhance the lift force by using other strategies, and we investigate structural constraint on motion amplitude. Thrust force modeling, we need to establish a model for estimating thrust force. I mean, if we have a model to estimate the produced lift force, we don't need to do experiment or to do microfabrication if we have this idea before providing the prototype. And we are working on second generation concept for further advancement. And this project was reported in France Television France 2 and Media, La Voix du Nord. If you could play the video, please, of this one.
Voici
Thank
le
you.
plus petit drone au monde. À peine plus de 3 cm d'envergure, un poids de seulement 22 mg.
Donc, it was on France 2 and France 3.
Difficile de capter leurs mouvements. Un
And on the
nanodrone
right side,
directement inspiré du vol des insectes.
on
Dit
print
biomimétisme,
media.
on va s'arrêter au mot
Eric Caton
bio-inspiration,
is
c'est-à-dire
professor in
qu'on
our lab, is
s'inspire
my
de la
colleague.
nature. L'idée principale dans notre travail, c'est d'essayer de
And we are
reproduire
working
ce
in
vol de
team
l'insecte, cette
with
cinématique
also
des ailes,
Sébastien
qui
Grandel.
aurait le maximum de portance. Donc c'est là où on dit on s'inspire de la nature.
Et pas facile d'expliquer de telles recherches à des collégiens. Eric Caton force
And
la pédagogie, lui,
Before, okay, this is my team, 3 professors, 3 PhD students, and me. And that's all for today. And thank you for your attention. And you who have, if you have questions, don't hesitate. Thank you very much.
Thank you for your amazing speech. And now it's time for questions from the audience. Do you have any questions? Może podajmy mikrofony. O.
Okay, so first of all, I want to say that your work is very impressive, your work and your team work. And I've got the questions about how you want to achieve the changing the direction of these micro robots with one actuator. Okay, so this is the first one, and second one, do you think about the mobile battery, let's say, which can be because this is, I think that's a very important thing, yes, in the mobile robot. Okay, so this is my question.
Thank you very much, sir. Thank you for your question. For the first one, of course, this nanodrone could not change the direction, and for this reason, we are thinking to add another actuation mechanism, and if we excite independently both of them, we can change its direction. For your second question, sorry. Batteries, yes, it's a good idea. Actually, we are working on this topic, but the problem actually is to find a battery with a minimal weight, because the most important in our case is the weight, and we are following research in this domain, but we are also thinking about using supercapacitor as a generator. Thank you, sir.
Any other questions? So maybe from my side, have you considered any other drive mechanisms in these actuators?
Okay, other drive mechanism.
Yes.
Okay, normally for this kind of prototype, we use two kinds. First, we can use piezo actuator system. We give a voltage or current, and we generate some displacement. If we use some amplifier, some mechanical system, we can first amplify the movement, because the piezo actuator movement is in the range of micrometer. We can use this technique. And second is this method, electromagnetic actuator. Maybe we can use other classical techniques such as DC motor or other low motor, but here we will get maybe a problem of the weight.
And the size of...
Yes, and the size, especially the size, because here we have nothing, only magnet and some spares with coil with diameter of around 60 micrometer.
Thank you.
Thank you, sir.
Szanowni Państwo, czy jeszcze jakieś pytania? Any questions from the audience? Okay, so thank you very much. Let's stay with us on the stage.
Thank you. Thank you.
And now we will go to the first panel, first discussion with experts. And I want to introduce our panelists. So the first one will be Professor Agata Bonenberg. She has researched into innovative technical and compositional solutions, including the use of biomaterials in architectural interiors. She has a special research interest in the application of modern research tools and methods such as oculography to empirical verification of architectural theories. Since 2020, she has been serving as director of the Institute of Interior Design and Industrial Design at the Faculty of Architecture of the Poznań University of Technology. Welcome. And the second one will be Doctor of Engineering Tomasz Machałowski, key account manager at Lohmann and Roscher, one of the leaders in the industry of disposable medical products for the operating room. Graduated of the Poznań University of Technology in Biomedical Engineering and Bioprocess and Biomaterials Engineering, scholarship holder of the German Academic Exchange Service. Welcome. And the last but not least, Professor Michał Rychlik. His area of research and activity mainly includes aspects related to computer-aided design systems, as well as biomedical engineering and application of computer engineering tools in medical and biomedical research. Welcome, Professor. And this discussion with our panelists will be led by Vice Dean of Faculty of Mechanical Engineering, Doctor of Engineering, Jakub Grabski. Welcome.
Thank you. So, thank you, Dr. Gena, for the interesting lecture, and thank you all the guests for agree to take part of this discussion. So, my first question is to Dr. Gena. What do you think? What can be the applications in the medical area of such nanodrones or similar technologies related to the medical applications?
Thank you. For applications of microtechnology or micro machine in medical fields, I think we have several applications. I will speak on myself. I'm working on 3 projects by implementing a kind of smart material in biomedical applications. I will give you an idea first. Actually, we are providing a kind of actuator with thickness of around 30 micrometer. This actuator is a kind of polymer actuator. When we give a voltage, it generates a displacement. And now, how we use, for example, this actuator for medical applications, we know if we have, for example, a cochlear implant, when the surgeon do the operation, it is not easy to insert the implant inside the cochlea. And in our team, we are working in order to provide smart implants. I mean, if we add, for example, several actuators along this implant, and if we know, for example, a trajectory inside the cochlea, and if we excite, for example, independently each actuator, we can facilitate its insertion inside the cochlea. This is one of the applications by using microtechnology process. The second, for example, application, actually we are supervising one PhD student, which is working with a robotic, is a startup located in Paris. And here we are using another type of smart material, which is shape memory alloy. When we give a current, it generates displacement and it has some memory effect. And the application is confidential, but is linked to drug delivery. And the PhD student is working on providing a kind of micro robots for drug delivery. And the idea, for example, is to use 3 wires of this shape memory alloy, smart material, in order to control a microsystem for drug delivery. This is second application. And third application, actually, I got project from ANR, Agence Nationale de Recherche in France, for doing research for minimally invasive surgery. I mean, at present, we have some micro camera in the commerce. For example, this micro camera has the diameter of around 0.3 millimeter. And idea is to provide a kind of smart endoscope. I mean, by using similar actuator, we can, for example, provide kind of micro gripper, and this micro gripper will be used in order to control the camera for smart endoscope. This, for example, task will help surgeons for doing their work. For example, when they do minimally invasive surgery, they need to move the endoscope, which is very rigid, and they need also to use second hand for doing the operation. And now, for example, if we have this smart micro-endoscope with controlled system based on microsystem with lower thickness, we don't need to make a big, big incision, and we don't need also to make several movement. This is my third application, I think. I think it's sufficient for today.
Thank you. Thank you.
Welcome.
So now we would like to go to the second area, to the architecture, and we have Professor Agata Bonenberg. So can you tell us some examples of the inspiration from the nature in your area?
Well, of course, we have been working with nature-inspired elements for a long, long time. We have been developing at the Faculty of Architecture elevation systems, facade systems that generates energy, that help to. They are mostly based on wind power. And these are the elements that then aesthetically mostly aesthetically show the connection to natural elements. What I would like, however, to underline after this really inspirational talk this morning, I would like to say that looking at the robots and micro-robots, they are machines. Their aesthetics, the way they look, are very heavily influenced, or basically influenced by how they work, what they do. And I would like to draw attention to the fact that the aesthetic of the product, the aesthetic of what we see, it is the way how we communicate with the general public, how we communicate with client, with the general public about our product. And how we modulate the emotions that the general public, that someone who looks at this, generates towards the product, towards the micro robot. So I would like to draw attention to the fact that also how we present, how we show this element is an important factor in how it will be perceived and whether or not it will be accepted by the general public. So I think it is one of the aspects that can be important when designing and when using the nanorobots, the robots, because we have quite a strong and, in my opinion, a particular cultural image of robots, of robotics, the cultural image that comes from science fiction movies and so on. And in this aspect, the opinion on the public opinion, the public image of robotics, is not always depicted as a positive one. So throughout the design, we can modulate emotions. We can either make our robots look friendly and to support this scheme of robots who help, especially in biomedical context. Or we can shape the robots so that they can look like something that is, for example, dangerous. So this is, let's say, our interest in robots, in micro robots, and how we perceive the aspect of the design.
Okay, thank you. I think that in bionics we can also say that it is not only inspiration from the nature, but it can be also using some natural materials. I think you can also say something about that. Okay?
Yes, we do have some experience with building with natural materials. We use, for example, substrate based on mycelium, so based on fungus. And we create elements of interior design, we create lamps, we create wall panels that are basically grown from the mycelium from fungus material. So we prepare molding, we prepare products, and this is our technology to create shapes and objects that that require minimal energy to grow and that are 100% biodegradable. It is the direction that we are now working in at the Faculty of Architecture in order to create objects that will have the same aesthetical level, let's say, as the objects that we can purchase from various shops and so on, but that they have this aspect of being completely, let's say, free of all of the negative sides of plastics and of I don't know, high energy of production that is connected with, for example, ceramic products and so on. So, and apart from that, I would like to underline that this aesthetics that is very natural in interior design is very trendy at the moment. It's enough to look at the products that you can obtain. So we are following this aesthetics. For us, it is very easy to follow this aesthetics because the finish of the material, the quality of the material, of the mycelium-based material has this aesthetics. So we are basically doing the natural thing. We are following this trend.
Okay, thank you. So now I would like to discuss about the next field of engineering, which is material science. And we have Dr. Tomasz Machałowski. So you was at the Biomedical Engineering Studies. So we have here also some people who study now biomedical engineering. And what is your experience from your studies, and what are your tips for the students which want to go into direction of biomimetics?
Okay, thank you for this question. Yes, I'm graduated biomedical engineering here in Poznań University of Technology. And which tips I can give you for your scientific way? First is to be brave. To don't worry about the fault. Be brave in your with your plan, with your science, and don't worry about the faults, because in my opinion the science and development is a matter of making conclusions after your fault. It's not constant success. It's never like this. So first, be brave. Second tip, it's be open for feedback, because sometimes we worry about someone tell us, okay, you do it it's a bad way. Don't worry about it. It's a good tip. So be open for these tips. Third, it's good to have some person who will be your sparring partner. I mean, the person which you can share your plans and which will be very objective for your everything what you are doing. And that's it, I think.
So what is your experience in biomimetics in the area, of course, in material science?
Okay, so all my scientific career was related with chitin and in general, natural materials in biomedical engineering. I'm really enthusiastic of natural materials in case of biomedical engineering because of few things. First is that natural materials are more friendly for our organism. They recognize it in most cases like something natural, and biodegradation and integration with organism is easier and should be easier than with artificial ones. So this is the huge advantage. Second, such materials are renovable. So it's also very important in case of application. What else? Natural materials have also other sides. Each metal have both sides. So when you look at that from scientific point of view, each natural products are similar but never the same. For science, it's a problem because when you're making some experiments, you need statistic and you have to see what sometimes small change make a big difference. So this is the little bit trap in natural materials. Then you have range. You never be each samples will never be the same. From the other side, natural materials and natural products are already have some structure. When you're doing something from artificial ones, you have to obtain it, and sometimes it's very costly. So I, in my research, use the naturally prefabricated materials, and I'm looking for that from different points of view to find the right application for them.
Thank you. And now we can also say some words about possible application of biomimetics in mechanical or biomedical engineering. Please, Professor Rychlik.
Yes, so the question was, sorry, that was able, like
yes.
Present? Yes, of course. We have present, but not very easy to observe them on this moment. Using the inspiration from the nature, because the first example, of course, this is a materials. So these materials, they are much more closest to the real nature, especially about the surfaces of the implants, that they will be in the same shape, in the same size, like parts of the bones in this nanoscale, that it will be much more connectivity, increase the connectivity between the real bone and this implant. Also, we have several extractions of materials from some special, for example, deep sea, let's say animals, but corals, that they could be a material to the implantation after special procedures of cleaning, of course. And another case, we are able to working with the shapes. And for example, we have some shapes that they are much more natural, much more organic, let's say, in the shape, in the design. You can imagine how it will be looks like the machine, like MRI or computer tomography, without all these plastic parts outside. So nobody from the patients would like to go inside, of course. So this is just a shape. But when we are talking about the optimization. For example, these shapes that we are receiving after optimization of the geometry, we are receiving something that the nature it's producing, because the nature by the 1,000 years they are optimized and to making this shapes, these forces, all how to say, environment influences on this components, the best test cases, and to choosing the best solution on the situation that exist. And of course, what it is all the time the promising that in the nature all the time exchanging our shapes, and our body is also changing when we will go to the space. Immediately our small workers inside us, they are changing our shapes, our bones, muscles, and so on. And the last example of this story, I can say that we are using the artificial intelligence. So what it is? This is also inspired by the nature of the neural networks. So they are working like neurons in our brain. So this is also like the like present in the biomedical engineering, but they are not so visible like we can thinking. So they are inside, for example, the softwares that they are making the automatic recognition of the biomedical imaging.
Thank you. And now maybe I have a question to discuss, because we have here the specialists in various areas of engineering, and you gave us some examples in your area about biomimetics. So can you see some area for collaboration between your areas of study in biomimetics? So maybe please, Dr. Sofian.
Okay. Yes, there is a possibility, and I forgot to mention that. I think in 2022, we have collaborated with Professor Witold, which is here. The project was, as in my perspectives, was provide a kind of model, for example, for predicting this lift force before doing measurement. And for this, we have supervised student, Carol, for doing this job, and we received them in our IML lab, and it was a good beginning, a good experience between our lab and the team of Witold. I think we have to find some common point, for example, from mechanical part of this insect, or in other perspectives for biomedical applications, applications of our smart material. Yeah, we need to apply for a project, and we need to get a budget for doing research together. Why not?
Any other examples? Okay. So maybe there is any question from the audience. Okay. Facebook? Okay.
Hello. So I also work in the field of designing, and I think it was a very nice point to say that to design a robotic devices, and in general, it's very important to also consider the user experience. So how people think of them. So for example, if we would only see in the television that the robots are killing machines, then definitely when we see in a hospital a robot that treats us, we would feel very scared about it. And this is not an accident why in all the studies we always ask people about the experience when they are collaborating or working with the robot. And I think this is the very important consideration, because otherwise we would not be able to transfer the scientific innovation into application, and especially in the field of medicine where the regulations are so strict. Yeah. So thank you. So this was not really a question, but rather like a point, also a comment to what was said before.
Okay, thank you.
So it was regarding this appearance of of robots and in our presence. So how we perceive them. I think it's a very interesting theme for designers. As I say, in robotics, there is not so much room to do that, because obviously they are so much related with with their mechanics, with all the other aspects of design. But I think still there is some space to make them make this perception of robots around us a little bit more friendly than what we are used to from this image that we have in general culture.
I also want to comment, because you told about robotic in hospital. I don't know if you know about it, but the hospital in general have a serious problem with infections. So each kind of automatization is a really good point, and is a future in my opinion. And the main transfer of these infections is of course people. So in cases and in a situation when some robots can do it instead of people, it's a good way for the future.
Okay, so if we are talking about the robots and medical and hospital, I mean medical robots. So of course we can say that there are two types on this moment already on the market. So you can use the, let's say, regular robot arms that looks like a little bit like from the industry, a little bit different shape, more smooth, let's say, and the colors, that they are much more medical. Yes, but they are working like on the operation room or in such kind of the closed areas that the patients usually they are sleeping. And the second kind that they are working a little bit like in our shops, that they are helping to giving some information, some hello, and keeping assistance like to taking, for example, using the monitor for making the connection with the patients and the family in the occasion that this patient cannot do this because of type of the disease, or because, for example, this is a senior and he don't know how to use, for example, the new technology of like multimedia or whatever. And of course, behind this, we can hide the systems that they are control the situation with the patients. I mean the parameters, temperature, some pressure, some aspect where we will use the artificial intelligence. We can make some interaction with the patients to checking the list what for something not correct with the psychic it's going. I mean depression or something like after disease. It can be happened with this patient. So this is a huge area that they are on the beginning of the row, but also there is a question how to should looks like such kind of the robot to be friendly and to be polite for view, for eyes, that we will be not scared about it. We can like this imagining this is big job in front of us.
Yes, I think it is basically a question whether we will see the moment, or when we will see the moment that robots can become the personal medical assistants, not only used in the strictly hospital context, but basically used also in everyday life, more closer to the, let's say, client directly or patient.
Yes, I will add one point regarding the use of some material in these robots. We are starting to think about using a kind of material which is, for example, biodegradable or also biocompatible in order to preserve nature. Also for the methods of fabrication, of course, in our case, we are using clean room environment. We are using several chemical products, and we are starting to think about how to preserve nature from this chemical product. And I think biodegradable material is very suitable for medical applications.
So on the end, I will close the loop because we start from the micro scale. Now we talk about the big robots. So I would like to say we can thinking about the biomedical engineering application of this small size nanorobots when we have, for example, the wound and for cleaning, for keeping the clean area and to protect the surface. So this is nanoscale and it can be done with the really nanorobots, for example. Thank you.
Thank you. Thank you all the guests for very nice discussion. And now I would like to give the microphone to Paweł.
To me, okay. Thank you very much. Wielkie brawa, big applause for our participants, our guests. We have some nice things for you. Thank you very much one more time for our panelists. And now we will go to our second session, but przejdziemy, Szanowni Państwo, na język polski, ponieważ kolejni nasi goście, kolejne prezentacje będą już odbywały się w języku polskim. Chciałbym teraz Państwa poinformować, ponieważ wyświetlił się kod z takim napisem "Odpowiedz na pytanie". Wspominałem już o konkursie wiedzy i to będzie konkurs, w którym po każdym wystąpieniu pojawią się 3 szybkie pytania do publiczności związane z tematyką zaprezentowanego wykładu. I Szanowni Państwo, za pośrednictwem telefonu wybieracie prawidłową odpowiedź. Waszym zdaniem prawidłową odpowiedź oczywiście. Te odpowiedzi mają charakter zarówno wielokrotnego wyboru, jak i jednokrotnego wyboru. No i oczywiście zwycięzcą zostanie ten, kto odpowie na najwięcej pytań poprawnie. Także warto słuchać i może nawet robić notatki. I Szanowni Państwo, wyniki zostaną ogłoszone jutro, po uroczystym zakończeniu konferencji. No i do wygrania oczywiście są nagrody, także to nie jest tylko tutaj dyplom, bądź też zadowolenie z tego, że się wygrało i dobrze słuchało, ale także będą jakieś upominki. Także, Szanowni Państwo, możecie śmiało sobie to przeskanować i odpowiadać na pytania. A tymczasem pozwolę sobie przejść do kolejnej sesji podczas naszego wydarzenia. Będzie to sesja, której tytuł brzmi Sztuczne narządy. Prelegentem podczas tej sesji będzie pan doktor habilitowany inżynier Maciej Gawlikowski, profesor Politechniki Śląskiej. Jest pan profesor? O, jest pan profesor z nami. Tytuł tej prelekcji to Droga do sztucznego serca. Pan profesor jest inżynierem biomedycznym i specjalistą klinicznym w dziedzinie mechanicznego wspomagania serca. W 2011 roku obronił z wyróżnieniem dysertację doktorską dotyczącą inwazyjnego pomiaru przepływów wewnątrzsercowych, a w 2023 roku uzyskał stopień naukowy doktora habilitowanego w dyscyplinie inżynierii biomedycznej. Mógłbym o panu profesorze bardzo wiele tutaj jeszcze przedstawiać, ale myślę, że prezentacja, którą nam przedstawi i opowie o swojej pracy, zrobi to sama za siebie. Także panie profesorze, zapraszam.
Dziękuję serdecznie. Chciałbym w pierwszych słowach, moi drodzy, podziękować za zaproszenie na tą wspaniałą konferencję, zarówno władzom dziekańskim, jak i organizatorom dzisiejszego spotkania. Bardzo się cieszę, że Państwo, młodzi naukowcy, doktoranci, magistranci tak tutaj licznie przybyliście, żeby posłuchać o rzeczach, które być może na Politechnice Poznańskiej nie są jeszcze robione, ale w Poznaniu, w poznańskich szpitalach już są stosowane. Ja zostałem tutaj bardzo ładnie przedstawiony. Pozwolą Państwo, że spróbuję, przełączyć slajd. Nazywam się Maciej Gawlikowski, reprezentuję dwie instytucje. Jedną to jest Fundacja Rozwoju Kardiochirurgii, gdzie jestem dyrektorem naukowym w Instytucie Protez Serca, a druga to jest Politechnika Śląska, Wydział Inżynierii Biomedycznej, gdzie jestem profesorem nadzwyczajnym, chociaż bardziej czuję się takim przeciętnym, prawda, profesorem. Zajmuję się inżynierią biomedyczną i mechanicznym wspomaganiem serca od 20 paru lat, zarówno jako inżynier biomedyczny, jak i jako specjalista kliniczny w tej dziedzinie. Uczestniczę w zabiegach operacyjnych, w prowadzeniu pacjentów, stąd wydaje mi się, że mam jakieś kompetencje, żeby coś tam Państwu sprzedać również klinicznego. Moi drodzy, moi drodzy, serce, to ktoś tam śpiewał najpiękniejsze słowo świata, wszyscy wiemy, każdy kto jest, był bądź będzie zakochany, czyli wszyscy z nas wiedzą Państwo, że serce to podstawa, tak, ale w pewnych przypadkach i to nie tak znowu rzadkich, nasz mięsień sercowy jako narząd, jako tkanka ulega pewnym dysfunkcjom. Proszę zobaczyć, tak wygląda normalny mięsień sercowy, przekrój przez nasz narząd pompujący krew, a tutaj jedna z wad tego mięśnia sercowego, kardiomiopatia rozczeniowa, kardiomiopatia przerostowa, kardiomiopatia gąbczasta, nazywana również kardiomiopatia zniescalenia, powodująca te i inne choroby, powodują pogorszenie stanu hemodynamicznego pacjenta i stopniowe pogarszanie się funkcji miokardium, czyli tej tkanki mięśnia sercowego. To leczy się oczywiście farmakologicznie, są różne w tej chwili nowoczesne metody leczenia, niemniej jednak następują pewne takie przełomy w historii pacjenta, okresowego zaostrzenia niewydolności serca, które pogarszają tą funkcję miokardium do takiego stopnia, że już terapie farmakologiczne nie pomagają i należy rozważyć zupełnie inne formy leczenia. Choroby serca są główną przyczyną śmierci pacjentów nie tylko w Europie, w krajach wysoko ucywilizowanych, ale również na świecie. Tutaj statystyki. W medycynie bardzo często posługujemy się statystykami, dlatego bardzo ważne jest, żeby wiedzieć, jakie czytać te statystyki i wiedzieć, o czym one mówią. Zobaczcie Państwo, że tu możemy zobaczyć, że choroby serca są główną przyczyną zgonów, natomiast nowotwory, których tak bardzo się obawiamy, jednak w tych statystykach plasują się niżej. Z tego powodu, mili Państwo, no nie wiem, nie umiem tego zmienić. Mógłby mi pan kliknąć zmianę slajdu? Może jeszcze raz? Tak, może zobaczymy, może ten będzie lepiej działał. O, bo tośmy się przesunęli dosyć mocno. Tak, jeszcze. Oj, jeszcze. A, tak konkretnie, tak? Nie wiem, chyba nie. Może będzie lepiej. Proszę Państwa, żeby leczyć tych pacjentów, żeby nie pozwolić im umrzeć, zakwitła kiedyś idea przeszczepu serca. Ten przeszczep serca został wykonany po raz pierwszy przez Christiana Barnarda w Kapsztadzie w Republice Południowej Afryki. To był 1967 rok. Co ciekawe, pacjentem przeszczepionym przez Barnarda był wówczas Louis Waszkański. Ja myślałem, że jest to Polak, ale okazało się, że jest to Litwin, emigrant, który przeżył wówczas No, niezbyt długo, tak, bo po 18 dniach zmarł na zapalenie płuc. Dlaczego? Dlatego, że otrzymując obcą tkankę, tak, otrzymując obcy materiał genetyczny, nasz organizm, nasz układ odpornościowy zaczyna się przed tym bronić. Uruchamiane są różnego rodzaju procesy, które powodują na zasadzie mechanizmu rozpoznawania obcych komórek w swoim własnym organizmie zwalczanie tychże komórek. Wiadomo było, że należy ten mechanizm ograniczyć, stąd cała nazwa, stąd pojęcie immunosupresji. W tamtych czasach nie było jeszcze zaawansowanych leków immunosupresyjnych, takich jakie mamy dzisiaj, na przykład tacrolimus, sirolimus, everolimus. Wtedy stosowano zupełnie inne terapie, przede wszystkim naświetlanie promieniami rentgena, glikokortykosteroidy, tutaj prednizon, stosowany do dzisiaj enkorton również w tamtych czasach był stosowany i proszę Państwa, wszelkiego rodzaju różne dziwne zabiegi, które miały na celu wyhamować ten układ odpornościowy, ale tak się nie stawało. Ci pacjenci najczęściej byli tak mocno zahamowani lekami immunosupresyjnymi, że umierali na różne zakażenia oportunistyczne. Dopiero pod koniec lat 70. Wyinstallowano z takiego grzyba w Norwegii, zupełnie, ale to nie te grzyby, o których Państwo myślą. Takiego grzybka w Norwegii wyizolowano cyklosporynę i w szwajcarskich laboratoriach udowodniono jej działanie immunosupresyjne. I od tego czasu rozpoczęła się era poprawnego leczenia immunosupresyjnego, tak aby pacjenci przeżywali dłużej w dobrym zdrowiu. Dzisiejsze przeżycia po przeszczepach sięgają, oczywiście serca, sięgają 23 lat, niemniej jednak mediana przeżycia nie jest specjalnie wysoka, bo w zależności od ośrodka i od kraju jest to 11 do 13 lat. Moi drodzy, w 1969 roku, czyli tuż po Barnardzie w Polsce, profesor Jan Moll dokonał, taka słynna rodzina kardiochirurgów, mam przyjemność znać następców pana profesora Jana Molla, czyli jego syna i jego wnuka. Pan profesor Moll przeszczepił serce w Polsce, w Łodzi. Niestety to był przeszczep nieudany, a Państwo tego oczywiście nie możecie pamiętać, ja to jeszcze pamiętam. Wtedy w Polsce mieliśmy zupełnie inny system polityczny i niestety odgórnie zapadły decyzje, aby wstrzymać programy przeszczepowe, ponieważ one nie są odpowiednio skuteczne. No nie mogły być skuteczne, bo był to przeszczep numer 1, więc nic dziwnego, że się nie udał. I tutaj, proszę Państwa, po latach przychodzi pan profesor Zbigniew Religa, którego spróbuję zaraz włączyć, który w 1985 roku w Zabrzu dokonuje udanego przeszczepu serca. Pierwszego udanego przeszczepu serca. Oczywiście nie od strzału, nie? Że przyszedł sobie do Zabrza, styknął palcami i nagle przeszczepik. Nie. Profesor Religa kilkukrotnie próbował wyprowadzać tych pacjentów, dobierać odpowiednie terapie, aż wreszcie za chyba 5. razem udało się ten przeszczep wykonać. Pacjent jakby nie żył zbyt długo, tak, bo tutaj to pierwsze przeżycie było 8-dniowe, ale ono otworzyło pewne zamknięte do tej pory drzwi i od tego czasu Zabrze stało się jednym z wiodących ośrodków transplantacyjnych w Polsce. Najdłuższy pacjent profesora Religi przeżył 26 lat po przeszczepie serca. To były czasy, w których ja zaczynałem karierę w Fundacji Rozwoju Kardiochirurgii. Miałem przyjemność, a chyba bardziej można powiedzieć, że zaszczyt pracować z profesorem Zbigniewem Religą. Był człowiekiem niesamowicie wymagającym. Muszę powiedzieć, że się go bałem, ale był przede wszystkim wymagający od siebie. Nie wiem, czy mój zespół, na szczęście nie ma ich tutaj, ale czy mój zespół moich naukowców również może to potwierdzić, że jestem równie wymagający, ale przede wszystkim zaczynam od siebie. Także od tego momentu zaczęły się, proszę Państwa, przeszczepy serca w Polsce. I teraz zobaczcie Państwo, jak to wygląda znowu na statystykach. Tak? Chcielibyśmy tych przeszczepów robić coraz to więcej. Niestety różne statystyki z różnych lat pokazują jedną niepokojącą tendencję, mianowicie liczba dawców, czyli ludzi, od których moglibyśmy ten narząd pobrać, ten i oczywiście wiele innych, bo pobieramy również nerki, płuca, wątrobę, rogówki i inne fragmenty ciała. Zachęcam Państwa bardzo do tego, żeby przemyśleć sobie w pozytywny oczywiście sposób to, że takie przeszczepy ratują życie nie jednego, ale kilku ludzi, a nawet jeśli nie ratują, to przynajmniej bardzo mocno zwiększają komfort tego życia i zwiększają przeżywalność tych osób. Warto nie zabierać swoich narządów do nieba, taka była akcja kiedyś. Zachęcam Państwa do tego, żeby pozbyć się jakichś ewentualnych ograniczeń związanych z dawstwem narządu. Jest to chyba jeden z najbardziej takich aktów humanitarnych, który możemy zrobić w stosunku do drugiego człowieka. I zobaczcie Państwo, że liczba dawców się nie zwiększa, pomimo tego, że, a może właśnie dlatego, że motocykle są coraz to szybsze, a liczba osób oczekujących na przeszczep jest coraz to większa. W związku z tym powstaje ta niezagospodarowana grupa ludzi, którzy prawdopodobnie umrą, jeżeli nie będziemy im pomagać w jakiś inny sposób, który sprawi, że oni doczekają do tego przeszczepu serca. I teraz, proszę Państwa, kiedyś w historii ludzkości zakiełkowała taka idea, że serce tak naprawdę pompuje krew. Kiedyś myślano, że tam się dusza mieści, no okazało się, że prawdopodobnie mieści się w zupełnie innym miejscu, ale główną funkcją serca jest pompowanie krwi przeciwko oporom, które stwarza układ krążenia płucnego bądź krążenia systemowego. W związku z tym, jeżeli ta lewa komora, która kurcząc się powoduje wyrzut krwi przez zastawkę aortalną do aorty i tam rozprowadza tą krew po innych narządach, jeżeli ta lewa komora jest niewydolna, to zastąpmy ją maszyną, pompą, która będzie w stanie przejąć część pracy, którą mięsień sercowy niewydolny nie jest w stanie wykonać i w ten sposób zapewni organizmowi ten przepływ krwi, który brakuje mu na skutek niewydolności i upośledzonej kurczliwości lewej komory. I proszę Państwa, taka idea jest no, w tej chwili funkcjonująca, tak? To już nie są jakby eksperymenty laboratoryjne, nie jest to koncepcja, jest to po prostu konkretne rozwiązanie technologiczne, o którym będziemy mówić, ale które nie wzięło się znikąd. Była jakaś droga, którą trzeba było przejść, aby z pierwszych eksperymentów przeskoczyć do terapii, którą dzisiaj stosujemy i która jest refundowana, o dziwo, w Polsce przez NFZ. Proszę Państwa, wspomagać możemy lewą komorę serca, tak? Wtedy mamy LVAD, czyli Left Ventricular Assist Device, lewokomorowe wspomaganie serca. Najczęściej występujące klinicznie, ponieważ ta lewa komora najczęściej ulega różnego rodzaju dysfunkcjom z tego powodu, że pompuje krew pod wysokie ciśnienie. Tak? Macie Państwo tutaj, jak siedzicie, młodzi jesteście, więc macie ciśnienie 120/70, więc jak uprawiacie sport, macie 170/100 powiedzmy. Pod takie obciążenie lewa komora musi krew wypompować. Prawa komora pompuje pod znacznie niższe ciśnienie, ponieważ ciśnienie w krążeniu płucnym wynosi kilkanaście maksymalnie milimetrów słupa rtęci. Jak Państwo zauważyliście, nie operuje w jednostkach układu SI z tego powodu, że historycznie w medycynie operuje się jednostkami zupełnie innymi i przezbrojenie umysłów lekarzy na myślenie w kategoriach jednostek SI nie ma najmniejszego sensu. Dlatego zostajemy przy takich jednostkach nietypowych. Napływ krwi do komory, do tej sztucznej komory serca może być albo z przedsionka, co jest w tej chwili już dość rzadkie, albo z koniuszka serca. W ten sposób możemy tą komorę sztuczną napełnić. Izolowane wspomaganie prawej komory, czyli Right Ventricular Assist Device, jest bardzo rzadkie, ponieważ wady tej komory są najczęściej spowodowane upośledzeniem pracy lewej komory serca. Można stosować również Biventricular Assist Device, czyli wspomaganie obu komór serca, ale to jest ciągle wspomaganie, tak? My nie przejmujemy całego przepływu, który serce generuje, a jedynie tą część, którą ono nie potrafi wygenerować, ponieważ miokardium jest uszkodzone. W pewnych przypadkach możemy zastosować całkowite sztuczne serce, total artificial heart. Te przypadki realizowane za pomocą takich pomp są stosowane również w Polsce. Ja pamiętam co najmniej kilka takich przypadków ze Śląskiego Centrum Chorób Serca w Zabrzu. No i krzyk mody ostatnio, nie tak oczywiście ostatnio, bo pierwsze doświadczenia moje z ECMO to jest 2010 rok, kiedy wykonywaliśmy takie eksperymenty na zwierzętach, badając takie właśnie systemy pozaustrojowego natlenowywania krwi, ale one również mają pewne znaczenie we wspomaganiu serca, dlatego o nich mówię. Proszę Państwa, to wspomaganie, jakkolwiek ono byłoby realizowane różnymi maszynami, urządzeniami, ono jest realizowane w kilku kierunkach, tak? I takim pierwszym kierunkiem to mamy mechaniczne wspomaganie serca jako terapia, jako pomost do przeszczepu. I to są najczęstsze przypadki, tak? Bridge to heart transplantation. Takie przypadki w Polsce są w większości wykonywane. Są też takie przypadki, kiedy pacjenci są w na tyle ciężkim stanie, że nie bardzo wiemy, co im wszczepić i nie bardzo wiemy, czy należy ich przeszczepić, czy przygotować do przeszczepu, a może już nie należy tej uporczywej terapii kontynuować z przyczyn etycznych, więc jest pomost do decyzji, gdzie za pomocą różnych urządzeń wspomagania serca, być może o niższym koszcie, ale spełniających swoje funkcje hemodynamiczne, potrafimy tych pacjentów wyprowadzić do takiego stanu, żeby zdecydować, jaką pompę im wszczepić i jak ich leczyć. Zauważono również, że w pewnych przypadkach, jest ich bardzo niewiele, to jest 1–2% przypadków, zresztą ostatnio to zniknęło nawet ze statystyk Intermaxu taki punkt, ale kiedyś ten punkt był obecny, to jest pomost do regeneracji. Zaobserwowano, że w przypadku mechanicznego wspomagania serca realizowanego pompami pulsacyjnymi, będę o tym za chwilę mówił, w niektórych przypadkach ta funkcja mięśnia sercowego jest przywracana. Tak? Oczywiście nikt nie mówi, że kardiomiocyty odrastają, natomiast wytwarzają się różnego rodzaju mechanizmy, które powodują, że ta kurczliwość lewej komory wraca do jako takiej wartości, która zapewnia pacjentowi jakieś tam powiedzmy życie na tych najniższych parametrach, ale jednak z własnym sercem. Proszę Państwa, następnie to jest destination therapy, czyli coś, co wiemy, że ci pacjenci nie kwalifikują się już chociażby z powodu wieku albo chorób stowarzyszonych, współistniejących do przeszczepu serca i wtedy na takiej pompie pacjenci żyją do końca swoich dni. To jest w tej chwili kilkanaście lat. Jest to jednak dla człowieka bardzo dużo, szczególnie dla człowieka, który jest już w sile wieku, że przez te naście lat może się zająć swoją rodziną, wnukami, pozamykać swoje sprawy, cieszyć się jeszcze życiem, a nie być przykutym do szpitalnego łóżka w oczekiwaniu na śmierć. To realizujemy albo za pomocą sztucznego serca, albo za pomocą tych urządzeń właśnie mechanicznego wspomagania. Te rzeczy tutaj, które są w tym zbiorze, to jest właściwie wyłącznie domena mechanicznego wspomagania serca. Jeżeli byśmy mieli głos, to proszę go wyłączyć, ale słyszę, że nie ma nic. Proszę Państwa, osoby wrażliwe, proszę o zamknięcie oczu na chwilę. To, co jesteśmy w tym miejscu, w którym jesteśmy dzisiaj, nie znaleźliśmy się przypadkowo. Tak? To nie jest tak, że Państwo sobie bierzecie telefon komórkowy i on powstał u Chińczyka, tak? Bo ktoś go kiedyś skonstruował. Kiedyś były Nokie, potem było coś tam jeszcze, aż dzisiaj mamy smartfony piękne i wydajne. Tak samo było z mechanicznym wspomaganiem serca. Zobaczcie Państwo, Siergiej Brukonienko, 1926 rok, bardzo dawno temu, to prawie 100 lat temu będzie, tak? Wykonywał eksperymenty na psach. Wtedy się eksperymentowało na psach. Dzisiaj oczywiście mamy takie obwarowania prawne, nie będę o tym mówił, Państwo to na pewno doskonale wiecie, że te eksperymenty są prowadzone w zupełnie inny sposób, ale wtedy czasy były inne. I wtedy eksperymentowano w taki sposób, że Brukonienko wykonał maszynę, która zastępowała częściowo pracę serca. Krew była natlenowywana przez płuca tego zwierzęcia i ten organizm żył. I to był przełom, tego nikt wcześniej nie zrobił. Ja wiem, że to wygląda makabrycznie, ale to dzięki takim eksperymentom dzisiaj możemy ratować nierzadko już dziesiątki tysięcy pacjentów, bo w statystyce Intermaxu ostatniej było 36 tysięcy pacjentów na mechanicznym wspomaganiu serca. Oczywiście w w okresie objętym statystyką. Więc takie były początki, tacy byli pionierzy. To był jeszcze kraj, który się nazywał Związek Socjalistycznych Republik Radzieckich. Dziś tego kraju już nie ma. I w tymże kraju niejaki Władimir Demikow w roku 1937 skonstruował właśnie taką maszynę zastępującą pracę serca. Zastosował ją w eksperymencie na zwierzęciu, 5 godzin przeżycia. W Stanach Zjednoczonych, w Yale, słynnym uniwersytecie, może ktoś z Państwa trafi do Yale, budowano takie urządzenia w bardzo prymitywny sposób. To, co Państwo widzicie na tym zdjęciu, to jest zabawka dziecięca, taki mały konstruktor, nie? I na tej podstawie William Glenn skonstruował takie urządzonko, gdzie piesek przeżył 90 minut podczas eksperymentu. To były jeszcze czasy, kiedy wschód wyprzedzał zachód, ale te czasy rychło się skończyły. Proszę Państwa, potem nastąpiła II wojna światowa i to jest osoba, o której ja nie mogę nie wspomnieć, mianowicie William Kolb. Ten facet ze zdjęcia, ten oczywiście starszy, tak? Czyli ten, wymyślił sztuczną nerkę, wymyślił dializator, kolumnę dializacyjną. To nie jest temat naszego dzisiejszego wystąpienia, ale to było w czasach wojny, II wojny światowej, gdzie ludzie ginęli masowo, a ten sobie wymyślił sztuczną nerkę, nie? I ratował w ten sposób ludzi. I w 1957 roku Kolb zaczął stosować różnego rodzaju materiały, biomateriały, elastomery, gumy silikonowe po to, żeby móc wlać do środka krew i pompować ją w sztucznych pompach. To jest kluczowa sprawa. Proszę Państwa, musicie pamiętać, że gdyby ktoś z Was trafił do branży kardiowaskular, to musicie pamiętać, że krew jest tkanką łączną, płynną. To nie jest woda. To się nie pompuje jak mleko w mleczarni albo jak piwo w browarze. Byłem tutaj w starym browarze z kolegą wczoraj, piękne miejsce, ale piwa tam niestety nie znaleźliśmy. Państwo pewnie wiecie lepiej, gdzie tutaj się coś można znaleźć. Pogadamy po wykładzie. I proszę Państwa, krew pompuje się w bardzo specyficzny sposób. Jest multum parametrów, których nie możemy przekroczyć. To są naprężenia ścinające, to są przepływy turbulentne, zachowanie przepływów laminarnych, unikanie kawitacji, nagłych zmian prędkości przepływu, obszarów zastoinowych i setki innych parametrów, które powodują, że przepompowanie krwi jest bardzo trudnym zagadnieniem. Należy ją przepompować nie tylko w taki sposób, żeby nie zniszczyć erytrocytów, nie spowodować hemolizy, ale przede wszystkim, żeby nie aktywować układu krzepnięcia, ponieważ układ krzepnięcia jest po to, żeby zatamowywać krwawienia wtedy, kiedy one są niepotrzebne. I jeżeli krew zetknie się ze sztucznym materiałem, to ta krew rozpoznaje, ten układ krzepnięcia to rozpoznaje jako coś nietypowego i zaczyna krzepnąć. I takie skrzepliny są dla pacjenta bardzo niebezpieczne. One powodują szereg różnych skutków ubocznych, łącznie oczywiście z jakimiś powikłaniami zakrzepowo-zatarowymi i udarami niedokrwiennymi, kończącymi się w sposób, który Państwo się spodziewają, prawda? Ale wróćmy do Kolfa, a w zasadzie w tej chwili do Adriana Kantrowica. Postać, która w życiu profesora religii odegrała bardzo istotną rolę, ponieważ był na stażu w Stanach Zjednoczonych u profesora Kantrowica. Kantrowic był znany wówczas w środowisku kardiochirurgów, wynalazł balon wewnątrzaortalny, to jest to, co Państwo widzicie tu. Taki długi balonik wprowadzany do aorty. On się napełniał w taki sposób, że był synchronizowany z pracą serca. W ten sposób wspomagał to po prostu serce, które było w częściowy sposób niewydolne. Do dzisiaj balony wewnątrzaortalne są stosowane jeszcze w kardiochirurgii z powodzeniem. Kantrowic wymyślił również tak zwaną łapę kantrowica, czyli kawałek mięśnia stymulowanego elektrycznie, naszywanego na tkankę mięśnia sercowego i który to mięsień był pobudzany, on się kurczył i wspomagał pracę serca. Religa wrócił wtedy bardzo zafascynowany czymś takim. Ja to oczywiście znam z opowieści tylko, więc mogę sobie pofantazjować w tej chwili, ale podobno wrócił taki zafascynowany, przyjechał do Fundacji Rozwoju Kardiochirurgii, którą stworzył i powiedział do naszego dyrektora, to słuchaj, zróbcie mi takie coś, nie? No i po chyba 4 latach rzeczywiście Fundacja Rozwoju Kardiochirurgii, naukowcy wytworzyli, wynaleźli, skonstruowali właśnie pierwsze takie mechaniczne wspomaganie serca w Polsce. Proszę Państwa, chciałem tu jeszcze wrócić do, do Debakeya. Ten człowiek, Micromed Debaki, potem była taka firma, która produkowała różnego rodzaju pompy krwi, ale on zastosował wspomaganie lewokomorowe, proszę Państwa, przez 10 dni. No to już przestały być eksperymenty na zwierzętach, to zaczęły już być badania, jakieś tam eksperymentalne, tak, ale jednak ratujące życie na ludziach. Debaki ze swoją, jedną ze swoich konstrukcji tutaj, którą Państwo możecie zobaczyć. Pyk. I następna człowiek historia, Robert Jarvik, to on to był biznesmen przede wszystkim, Jarvik, nie? Był inżynierem, współpracował z Kolfem, słuchajcie, zmodernizował to jego sztuczne serce, zmienił materiały kompletnie, uzyskiwał lepsze biozgodności, tak? Ale jednocześnie był inżynierem, który był biznesmenem. I troszkę tam podprowadził temu Kolfowi różnych pomysłów. Otworzył firmę i zaczął produkować takie właśnie sztuczne serca, jakie Państwo możecie zobaczyć tu. To się nazywało Jarvik 7 wówczas, 82 rok. To już były czasy, kiedy nie można sobie było wszczepiać, jak tam się, prawda, chciało, tylko trzeba było mieć odpowiednie zgody. W Unii Europejskiej nie wiem, jak to było w tamtych czasach, ale w Stanach Zjednoczonych istniało FDA, czyli Food and Drug Administration, agencja rządowa regulująca to, co można wszczepić, co można zastosować u człowieka, kiedy, jak, gdzie i tak dalej, i tak dalej. I teraz, proszę Państwa, Jarvik zaczął sobie to wszczepiać. Zobaczcie, że już rozkręcił na tym mało seryjny biznesik, tak? Dlatego, że mamy 90 przypadków, to nie jest mało. Niestety Jarvika w tamtych czasach pokonały procedury. Proszę Państwa, wytwarzanie takich urządzeń jest bardzo skomplikowanym procesem technologicznym. Jarvik nie miał potencjału do tego, aby ten proces stworzyć w sposób technologiczny właśnie. Żeby ta produkcja była, żeby to była produkcja, a nie manufaktura. Żeby to było powtarzalne, żeby to było bezpieczne, żeby to się brało z półki, wszczepiało pacjentowi i cześć. I proszę Państwa, z powodu tej słabej kontroli jakości, słabemu nadzorowi nad produkcją, FDA cofnęło mu tą zgodę. Dzisiaj, w XXI wieku, mamy normę ISO 13485, która mówi, jak należy wytwarzać wyroby, w szczególności medyczne, tak, żeby ta produkcja była powtarzalna i żeby jakość każdego z tych wyrobów była taka sama. To prawdopodobnie uratowałoby Jarvikowi pewną część ciała, gdyby ta norma wtedy była. Niezależnie od tego, jak te systemy wspomagania serca są zbudowane i kto je produkuje, to składają się z pompy krwi, czyli czegoś, co ma bezpośredni styczność z krwią i wymusza ten przepływ, czegoś, co tę pompę napędza, silnik elektryczny, a może sprężone powietrze. Był kiedyś pomysł na zrobienie nuclear heart, czyli sztucznego serca napędzanego energią atomową. No dzięki Bogu nikt tego nie zrealizował praktycznie. Coś, co steruje tą maszyną i coś, co ją zasila. Te 4 komponenty w każdym z tych rozwiązań istnieją, tak? I teraz, proszę Państwa, chciałbym pokazać, że w zależności od tego, jak bardzo my chowamy to sztuczne serce pod skórę, tak bardzo te wszystkie komponenty pod tą skórą się muszą znaleźć. Im dłużej wspomagamy pacjenta, chcemy go wspomagać, tym więcej rzeczy powinniśmy mu pod skórę do brzucha albo do klatki piersiowej wsadzić. Jest to problem, ponieważ tam nie ma za dużo miejsca, u mnie jest, tak, ale tu u Państwa widzę, że nie za bardzo. Więc trzeba skonstruować to w taki sposób, żeby to wszystko było miniaturowe, a to oznacza, że się będzie grzało, a jak to zasilać, a jak to tam wsadzić, a jak to wszczepić, a to musi być małe, a jeszcze trzeba by to było jakoś sprawdzić, czy to funkcjonuje i tworzą się dziesiątki komplikacji, o których dopiero się człowiek przekonuje, zaczynając budować tego typu urządzenia. Adawa kadabra. No i co? Nie czaruję, jak w Hogwarcie. Dobrze, tutaj mówi się, że od przybytku głowa nie boli, ale ja tutaj napisałem, że prawda, głowa boli, bo tych różnych typów sztucznych serc było bardzo dużo. Ja przedstawię Państwu pokrótce tylko te, które znalazły jakieś zastosowania kliniczne, no bo oczywiście od laboratoryjnych rzeczy no nie będziemy tego robić. Skoro tamto nie zadziałało, to będzie teraz expecto patronum. Ale też chyba nie zadziała. Mógłby mi Pan O, jest. Pierwsze były, proszę Państwa, takie systemy pulsacyjne, tak? Taka dziewczyneczka tutaj, malutka, dzieci też się wspomaga. Siedzi na maszynie pneumatycznej nazywanej Big Blue, a tutaj ma sztuczne serduszko. Tu. I się śmieje. To jest po prostu, mnie to zawsze rozwalało, nie? Takie coś. Proszę Państwa, pierwszym takim systemem był amerykański, a czyjżby inny, system firmy Toratec, nazywał się PIVAT, Pneumatic Ventricular Assist Device. Ja zawsze będę pokazywał X-ray, znaczy zdjęcie, jak to wygląda podłączone do mięśnia sercowego. No sami Państwo widzicie, że jest to dosyć duże, tak? Te komory wystają na zewnątrz, ale dzięki temu można je wymienić, nie rozkrajając pacjentowi klatki